So welcome to the today's lab. Today, this is the fourth lab, right? Okay, this is the lab number 4. So let us see the modeling of. We have all in the last class, in the last lab, we have seen how to model the structural modeling of the full adder, right? Today we are going to see the various modeling styles on decoder, right? Because we are going to talk about many more things on this simple 2x4 decoder with all modeling styles and what are the different things that we need to learn from that modeling, right? So let us keep heading modeling of 2x4 decoder. Okay. Okay. What we know about the 2x4 decoder, we have seen in the second year DLD course, right? So what we have learned about the 2x4 decoder. My voice is not clear. Okay. Right. What is the 2x4 decoder? What is the functionality of the 2x4 decoder? If you take something like this, for example, you have okay. Let us consider the input is A here, the input is B here, right? How many outputs you will have? It will have the 4 outputs, right? Let me call it, this is D0, this is D1, this is D2, this is D3, right? So this is the block diagram of a 2x4 decoder, right? So what is the functionality? What is the functionality of this 2x4 decoder? What is the functionality of this 2x4 decoder? If A is 0, 0, then we have to consider about all the outputs D0, D4, D3 to D0. Okay. At a time, only one output will be logic high, remaining all are logic 0, right? So let me write that the truth table here also. If this is the A here and B here, let me consider D3 is my MSB bit, okay? And D2 is my LSB, and something like this is go on. And D0 is my LSB. So D3 is MSB and D0 is LSB. Now, if you apply 0, 0, what will happen to this? It will be 0, 0, 0, 0, right? I'm so sorry. This will be logic 1. If it is 0, 1, it is 0, 0, 1, 0. If it is 1, 0, 0, 1, 0, 0. If it is 1, 1, 1, 0, 0, 0, right? As you know, this is the truth table. What are the mathematical equations to get the hardware for this one? As you know, the hardware, if you want to get this one, if you want to get this midterm, if you want to get this midterm, you have to take, this is what the input is responsible, right? So this input is responsible. This input is responsible, okay? Let me write that equation. Okay, D0 is actually A bar dot B bar, agreed? Next to D1, D1 is A dot B bar. D2 is, I'm so sorry, I think this is not that. Is this right now? A bar B should be. Next, this is A dot B bar. D3 is AB. Now we know everything in the fundamentals about this 2x4 decoder. Its block diagram, okay? What are the inputs and outputs and how it behaves, okay? By applying some inputs, what is an outputs? And then what is the mathematical equations that are required to what is the inside of that particular block diagram. Okay. Now, based on this particular basic understanding, let us go and write the Verilog program for it. So, in all the three modeling styles. Okay. Let us start simply. Let's start with which one you feel better. It's very easy. Data flow model as usual because equations are very less number of variables here we have. So let us go and write that. Okay, let me start the module. What is this name of the module? Let us give decoder DEC. Let me write in the lowercase letters, and all the time we don't want to forget that one since it is a case sensitive. DEC underscore 2 by 4 underscore DM. DM stands for data flow modeling. That's what the identification I have given. What are the inputs here? Sorry, what are the variables I'm using? A1 variable, B1 variable, D0, D1. So let me write all these things in the MSB to LSB. That is a better way. Therefore, D3, D2, D1, and D0. Okay. Now, what are the inputs out of these variables? Inputs are A comma B. Okay. Next output is D3, D2, D1, and D0. Right? What are the equations that I have to write? How equations can be write in Verilog program? By using the assignment statement. Assign D0 is equal to not of A ended with not of B. Right? A bar, B bar. This is how Verilog operators we have to use. Okay. I can copy this equation. How many times? 3 times I can use it. Okay. If you want to keep it, the parenthesis also is not a problem. You can also make use of that one if you're not you're confusing, right? Okay. So let me take this particular statement, copy another 3 times. Okay, what is the modification I have to see here? So not is required at this place, right? Here is not is required at this place, and here both we don't need any kind of not operation. And one more thing is that here also we have to change these kind of things. This is what actually D1, D2, D3. Okay, and finally end this module. Right? Okay, this is the data flow modeling of 2 by 4 decoder. So now let us take another program. Okay, that means same thing we would like to model using okay, the structural modeling. Okay, okay. Structural modeling here in this case is just directly by using the only the gate consisting of only 2 inputs. Okay, 4 gates we consider, and we make use of those 4 things. Okay, so let me take the diagram for this. Okay, therefore this is what the prerequisite is required when you are writing the okay, data flow model. Okay, what is the prerequisite for this structural modeling, or I can say simply a gate level modeling in this case? GM. Okay, that means gate level circuit is required. Okay, what is the gate level circuit? As simply something like this. We have to consider one variable A and we have to consider the complement also, right? A bar is also required, right? We take A bar. Next, we have to consider B, and B bar is also required. And then now, right, and how many AND gates are required? 4 AND gates are required. 1, 2, 3, and this is 4. Okay, so let me consider this is called D naught. Let me consider this is D1, this is D2, and this is D3. Okay, so simply we can write here is this one is connected here. This one is connected here, and of course, sorry, this is also connected to this one. Similarly, B is required here, and A bar is required here. Next, A is required here, here, A bar is required here. Here, A is required, B is required. Hopefully, this is what the logic diagram for the gate level circuit for the 2x4 decoder. Let us write which equations are required here. Do we have any change in the external variables and then internal input declaration, output declaration? There is no change, right? Only change required here is the internal view. Okay, so let me write, let us go and modify this. Okay. So let us write the name of the gates. For example, this is called the G1, this is called G2, this is called G3, this is called G4, this is called G5, this is called G6. Okay, 6 gates that are there, right? Inside of it. Okay. So what is the first gate? That is, how can I write the first gate? Simply we can use the not is the keyword. The name of this gate is G1. Okay. What I have to write here now? First of all, output. What is the output for this A bar? We don't have any, there is no name for it, right? So let us give one name for it. This is called, suppose for W1. Okay. This is W2. Assume that the W1, W2 are internal to the block. Internal to the block, whatever the variables that we use. So therefore, let me write here is W1, comma, A. Okay. Now, we'll take another NOT gate. Okay, take another NOT gate, Z2, W2, comma, D. Since we are using these particular variables, W1, W2, we have to declare them as void, right? So let us write the voids here somewhere. Okay, let me take, this is a little bit down, and then void. Void W1, comma, W2. W1, comma, W2 are the voids. Next. 4 gates are required. Okay, let me write the 4 gates here also. And G3. What is the output here now? D1, comma, W1, comma, W2, right? Right like this. So I'm talking about this gate. Okay. What is the output here? D0. What is the input here? W1 and W2. D0. Yeah, it's a D0, right? Sorry, it's a D0. Right? So just I want to copy this one for 4 times. I want to copy this. Copy 4 times. While you're copying this one, you have to change the labels, the required names, right? Okay, just don't keep it like the same thing, right? So it is actually G4, G5, G6. So what about outputs? Output I need to change. This is actually W1, D1, D2, and D3. What about here now? I need to change somehow with this kind of things, right? Okay. Uh, Tell me now. W1 comma B. Very good. Next. W2 comma A. Very good. A comma B. Excellent. Right? This is the gate level modeling for the same 2 by 4 decoder. Right. Let us write a structural modeling. Sorry, behavioral modeling. Right? In the previous class, in the behavioral modeling, we have used if statement, right? If else statement we have used. But today we are going to use another procedural statement that is called case statement. Okay. So let us write that one also. W1, W2. We have mentioned here, no? Okay, it's a white that we have mentioned. We have declared them as a whites. Yeah, whatever the name before. Without writing any whites. Yeah, we can write the code also. Without writing the W and W2, we can write. Okay. So how I can write something like this, I can write. Okay. It is possible, but I'm not going to, this is a too early to talk about that one. But this is called right, not of A comma, A, I can write it here without writing the W1. Okay. Are you getting the point? Okay. So wherever you are finding the simply W1 is actually the complement of the A only, W1. W2 is the complement of B. That's the reason why operator is available with you. You can make use of that one. Okay. There is a possibility is there. Okay. So just for the habituation of if the internal bytes that are there, then we are able to write this in this way. Hmm? Okay. Keep it like this only. Okay. Now the same program I want to copy in order to write behavioral modeling for it. Copy. I want to paste here. Okay. So what is the prerequisite for this to write? It is required this one, right? Let me go and take that one. Okay. So what is the possible modifications I have to do it here? Let me call this is a behavioral model BM. Okay. And very important that all the outputs must be represented by a registered data type. Don't forget about that one. Which is a keyword that I have to use. And then you have to modify the internal circuitry. Delete this. So what is the first thing that I need to write? If you want to start a behavioral model, what is the first thing that you should write? Always statement, right? Let us write the always. Always at the rate of So input changes, the output will change, right? So therefore the sensitivity should be input variations, A comma B, the input variations. Let us start begin here. And then we need to write end at this place. Somewhere you can write the end module here. Sorry, and begin and end. So I'm going to write in between. As I told you that we are going to use one procedural statement that is called case statement. Okay. Let's take a case statement, something like this. Case. So I want to see always this is the one, this combination is the one case. This is the second combination is another case, and third combination is the third case. Fourth one is a fourth case. Okay. I want to see these two things as single. I want to group these two bits as a single. Okay. How do we make this one? With the help of concatenation. With the help of concatenation, I can group these two things, right? A comma B. Better I can write A comma B. Okay. So I want to see these individual bits as a single variable. Okay. Okay, fine. Now, if AB is, what is the size of the AB now? AB, A comma, concatenation A comma B becomes, it's a 2-bit size, right? A is a 1 bit, B is a 1 bit. When I concatenate these two things, it become 2-bit size. Okay. So therefore, let me write the 2-bit size. 2-bit of 0, 0. Okay. If this is the case, what should be the output? How should be D naught is equal to D naught should be 1 and D1 sorry D2 D2 D1 D2 D3 are zeros. Okay. That means how many statement I should write? Something like I should write, right? D naught is equal to 0, 1 bit of 0. Okay. Next to D1 is equal, something else I have to write 4. And one more thing is begin and also I have to write, right? So let me write here in this way. You're not don't confuse. Let me start. Since it is a 4 statements I need to write. That's the reason why. Begin here. Begin. Now we can start D naught is equal to 1 bit of 0 and D2 is equal to, so D1 is equal to 1 bit of sorry, it is this one, right? This is 1, this is 0 and D2 is equal to 1 bit of 0 and D3 is also 1 bit of 0. This is how I need to write. And finally, I need to write here is the and. This is for one case. If you want to write the second case, for example, I have to repeat the same thing. Okay, instead what I can do, I'm going to modify this thing something like this. For the second case, I want to modify. Okay, 2-bit of 0, 1. I'm going to write in this way, effectively. I'm going to concatenate D3, comma, D2, comma, D1, comma, D0. Okay, something like this. This is a 4-bit size, right? The 4-bit of 0, 0, 1, 0. So this is the simplest way that I can write. Are you getting the point? Just equation, whatever it is, the equation is there, that sorry, that whatever the truth table contents that are there, the truth table contents only I have placed here. If 0, 0, and this should be 1, 0, 0, 0. Okay. Next, if it's 2-bit of 0, but instead of writing this, the 4 statements with begin and end keywords, just I can write only single line statement. Okay, with the help of concatenation. That's the advantage of using the concatenation. Okay. For example, just for the simplicity, I'm asking you something like this. If I copy and paste this the same thing, okay, what is another simplest way that we can do it here? If I'm keeping this the same thing here, okay, let me do one thing. Let me keep this is a little bit lower. Just I'm asking one simple question. If this is, for example, 0, 1, for example, okay, I want to use the same thing only. Okay, what is the modification I have to do? D naught is equal to 1, sorry, 0. D1 is equal to logic 1, and remaining all are zeros. Okay, so here only what is the change that we observe here? Only this value changing, this value changing, right? The remaining two are not changing. That means it is possible that you can remove these two things also. Okay, because if these two are not changing, definitely what is happening here? Definitely what will happen? It is possible to write in this way also. This is a 0. This becomes 1. Because already I have declared that those things I have mentioned that 0 and 1, it's not changing. Yeah, what I'm saying that already we have, this is assigned with 1, logic 1. It is already logic 1 is assigned to it. What is the default value of the, suppose a variable A is there, okay? One variable line here, something like this. If this particular net is declared as a register data type, register A, if you write like this, then what is the default value of this net? That's the question. The default value of this net is unknown. What is this value? Unknown. This white can be a 0 or it can be a logic 1. We don't know. But maybe 0, it can be 1. Since it is this net is declared as registered data type. For example, if this net is actually, if A is declared as wire, for example, wire A, if you like this, the default value of this one is high impedance state Z. It will be high impedance state Z. Okay. That means there is no connection actually. Okay. But whereas if you write it as a registered data type, it can be logic 0 or logic 1. Unknown value will be there, right? So therefore, if you see very carefully at this point, if D0 to D3 are declared as a registered data type, which means that by default, these variables holds unknown value. Okay. Okay. Now here look at this one. In the first case, I changed all the unknowns into, look at this one, all the unknowns into 4 unknowns, right? Okay. This is called D3, D2, D1, and D0. So all these unknowns are converted into known values by in the first case. Okay. Now this becomes, this is 0. Sorry, this is the 1. This is 1. This is 0. This is 0. This is 0. This is how it becomes. The first case is over. Okay. What about the second case? Now again for the second case, the values of D3, D2, or whatever the D3, D2, D1, D0. Since it is a registered data type, these values are assigned to it already. Okay, what are the already available things here? This is a 1, this is 0, this is 0, this is 0 available. Since it is a registered data type, already stored that values. Now in the second case, I change something. What I change here? This to 0, this to 1. I'm not declaring anything here now. That means that whatever the values that are there, that will be keep it like that only. Is this point is clear? Okay. Right. So in the third case, so since it is, even though if you write, whatever the unchanged things that are there, if I'm keeping like that, it's not a good advice. Okay, better we can go and simply, this approach is far better. Do you agree with me? This is very simple. We did not worried about to write a begin and end block. Okay, just simply we can write it as it is, right? So therefore, this is actually, let me write, I want to change this one to 1, 0. Okay, next I want to copy the same thing. Okay, I will change the output also. Just be hold. Okay, next, change block. Okay, next, this is must be changed. This to 1, 0, 0, 0. What about this one? This is 0, 1, 0, 0. Hopefully you catch this point, right? Okay, that is another one point. And the last step in this, the case statement, the procedural case statement is we have to write, we have to use the end case. Okay. Of course, before going to the end case, we have to write something. Okay, let me write the first end case, then we'll talk about that one. End case. Yeah, this should be 1 1, right? Very good. It should be 1 1. Okay. So before the end case, we have written the 4 cases. Okay, but by in fact, it's not 4 cases. It should be more than the 4 cases. Why it is more than 4 cases? See, as you know that Verilog is a 4 valued system, right? That means A, if you take A, so far we have seen that only it have 0 value, 1 value it can take. But it also can take unknown, it also can take Z. Similarly, B also another line. Okay, B also can take 0, 1, unknown, Z. Okay, that means if you have only 2 possibilities of A, if you consider only 2 possibilities of A, then we can simply say that it is a 2 power 2. That is 4 combinations we can apply. Okay, but it is a base is actually a 4 value. Okay, therefore, how many possible combinations I should apply? Since it is a 4 valued, that means the base is 4. 4 digits I'm using 0, 1, X, and Z. Such value variables are 2 we are using. Okay, 2 variables A and B are 2 variables, right? 2 we are using. Okay, therefore, now it becomes 16 possible combinations. Okay, that means how it will start. It start with 0, 0, 0, 1, 0x. Therefore, this is called A, for example, A, B, something like this, and 0, Z also. That means B also can take all the 4 values, right? Similarly, A can be 1, and this is 0, 1, 1, 1, x, 1, z. Similarly, A can be x, B can be 0, A can be 1, sorry, x, something like this also. Like this again, we have Z0, Z1, ZX, ZZ. So all are 16 possible combinations. We are not writing all the 16 possible case related output. Okay. So by default, some value we can keep it like this. Therefore, we bothered only. So this part, this one, and this one. All other things we did not worried about it, right? So for all these cases, what I know these values, right? I know this value is 0, 0, 0, 1. I know this value is 0, 0, 1, 0, and this is 0, 1, 0, 0, and this is 1, 0, 0, 0. But all other cases we can keep it some value. What we can keep it some value? For example, all are unknowns. For example, look at this one. So if somehow if the tool will enter into this particular uh, combination, it can be x x x x, and it should be shown, or maybe all zeros, or maybe all z's, all ones, whatever the name that you can whatever the value that you can keep it here, it will be same. But how do we represent that one? That is done with the default case. This is called default. This is a keyword that we have to use. For default case means is that other than these 4 combinations, remaining all combinations. Yeah, we have to. So since there is a possibility that we have 16 possible combinations are there. Since 2 variables we are taking, each variable take 4 values means that we have 16 possible combinations. But out of 16 possible combinations, we are declaring definitely we are writing only 4 combinations. For all other combinations, we are calling as default case. And for the default case, we pick some values. Okay. So for the default case, what I'm doing here, for default case, it is mandatory that you have to write it. Okay. D3, D2, D1, and D0 should be some some unknowns. Okay, some unknowns it will be showing. But you cannot see this kind of the value. But by default, if you enter into any other other than this 4 defined values that we have seen in the truth table. For all other cases, it will be unknown. It's a good practice that if we have a possibility, that means if suppose in this particular classroom we have a two doors are available, okay, you don't want to allow that particular door to enter into this particular lab. Therefore, you have to open this one, you have to close this one, right? Definitely, you have to do something. Okay. So the possibilities that are there, if the possibility is not there, you don't worry about it. Whether locking that one is not, it's a meaningless question. When we have a possibility, you have to define what about the other case. If you open this one, you want to open that one or not. That's what it is required. Are you getting the point? Yeah. So this is how we have to write the case statement. Hopefully, every detailed information that you can see from here. Yes. So in the hot water, if you're using the case statement, definitely you have to write the default. If you're not writing the case statement, if you're using the if else statement, you're not worried about it. While. So while I did not discuss this one, so we'll talk about that. Why should we mention only here? Yeah, because this is because of the case statement. According to the case syntax, we have to give all possible cases. Okay. So there also actually, suppose if you are not writing, for example, something like this. Okay. But actually everywhere that we have to write. Okay. Since you asked, let me write it this way. For example, if a equal to 0, I'm writing here. A equal to 0, I'm writing here. Okay. Then you write begin, y is equal to 1 bit of 0. Else, if you write else, then what will happen? If you write else, y is equal to 1 bit of 1, you are writing here. Okay. If a equal to 0 means that we have defined only one possibility. But how many possibilities that are there? Another 3 possibilities. A can be 1, A can be unknown, A can be Z. For all other cases, for all other, else stands for any other value of A, it will be 1. Okay. If I write like this, if else if, for example, A equal to 1, I'm writing here. The output is something like this. Okay, that means else if I write like this, then y is equal to 1 bit of 0. Suppose unknown, for example, it's unknown. What does it mean? In this case, what is the other possibilities? Unknown and x. Already I have defined a is 0. Already I have defined 1. Then remaining tails stands for other combinations of a and b. Okay. So therefore, by default, we are writing all. So even if you're not writing this statement also, even if you're not writing anything this also, if statement we have written, for this if I have already written something here. Else statement for this one, I have not written any kind of else statement here. Else statement I have not written here. So by default, that values are unknown. By default are unknown. Okay. So therefore, for whatever, if suppose if A can go to the X or A can go to Z, for example, then what should be the Y here? Y should be unknown only. Why it is unknown? Because because Y I had declared as registered data type. That's the reason why it becomes unknown. Suppose if you are defining something like this, for example, okay, I don't want to keep it something like this, for example, else y is equal to z. Okay, yes, instead of you writing x, you are writing z here. If you say that else y is equal to z, means that output will show you the z only, z value only. It won't show x. If you're not writing this one, what you can understand? Y value will be unknown. Okay, therefore, else statement by default, if you're using if statement by default, else statement will take for any other possible combinations, it will be unknown only. Okay, so but instead of doing this kind of approach, better we have to go for the case approach. it will definitely mention that we have to definitely write the default statement. And for all the default cases, it will be given. Okay. Yeah, that's what we can understand. Right. Good. Okay, so this is what we have to written almost all possible three modelings, right? But I want to modify something here. Please look at the modification part. Okay. Okay. What we have to do here, see, since this particular logic block has two input variables and four output variables. Okay. But what if the input have got, for example, 16, 32, or 64 inputs? Output is also 64 output. Then is it possible to write A is A, B, C, something like this? We'll go and write. It's not advisable. Instead, what we have to use, we are going to use vector notation. We're going to use vector notation. So we are going to write vector notation. What is this vector notation? So since whenever you are giving this individual line something like this is called a scalar notation. It is called scalar notation. We want to use this scalar notation into a vector notation by simply take one line here and mention how many or what is the size of this line. This is a 2-bit line. Okay. Now I'm going to write A here. I get to the point. Instead of the two lines, I'm going to write one line having 2 bits. Okay. Similarly, I'm going to use another line here. What is the size here? 4 size and D here. Get to the point? Okay, good. Now, what is the representation of this one? Usually, the moment if you write A here, you should write something like this. So if A is a 2-bit line, we have to write A of square brackets 1 down to 0. Something like this we need to write. We have to write A of 1 down to 0. So this is the 2-bit line actually. Okay. So that means that MSB bit is actually MSB bit is A of 1, and this is the one line. A of 0 is another line. Are you getting the point? Okay. So actually A is actually 2-bit size. It is represented by A of 1 down to 0. What are the individual lines here? A of 1 is a 1, A of 0 is another line. Okay, good. Now, for example, just you want to mention the two lines, two lines. That's it. Okay. It can be something like this also. A of okay, now it becomes MSB actually. It is MSB. This is LSB. Okay. This is MSB. This is LSB. And similarly, if I write 0 to 1 also, right? This is also possible to write 0 and 1, 2 lines only. Therefore, now here, what is the MSB here? A of 0 is MSB. A of 1 is LSB. Are you getting the point? Okay, this is also possibilities here. Or otherwise, you can also write, for example, something like this. A of 3 down to 4, for example. Here also we can write 2 lines only. The difference between the 3 and 4, how much? Only 1. Okay, 400. But actually, individually, 2 lines that are there. Okay, something like this. A of 3, A of 4. So this becomes MSB. This becomes LSB. Okay. For example, if I write like this, A of 7, 5. So how many lines that are there here? 2 lines. Yeah. So how many lines we have here? Three lines actually. A of 7 is one line. A of 6 is one line. A of 5 is another line. Okay. This is the range actually we have given. Okay. Please remember that this is the range actually. 3 to 4 is the one range, or 7 to 5 is the range, or 1 to 0 is a range, or 0 to 1 is a range. We are giving the range. Okay. What is the highest value? What is the lowest value? During that one, there is a difference. Okay. So usually these are all the possibilities that are there, but we always use this particular approach. Okay. So MSB means that high value that we'll give. LSB means that low value will give. Okay. So therefore, since it is a 2-bit line, right? Okay, that's the reason why one is the maximum value of MSB is 1. Lowest value of the line is 0. Did you catch that point? What? Ah, we should not write it for unknown and z case. Okay, this is a known, the giving the numbers to it. Okay, this was the variables, right? Variable cannot be x and z. Right? Okay, variable can be x and z, but it's not values actually. It's variables actually. So please remember that this is a variable. This is the variable. A of 1 is a one variable. So this is actually equivalent to this one, for example. A of 0 is one variable. This is a B, for example. So something like this also you can write. For example, x of 1 down to 0, for example. What does it mean? X of 1 is a one line, and x of 0 is another line. Here x is not a value, it's a variable actually. Okay. So please remember this point also. Whenever you write an x and z of your alphabets, not for variable purpose, use for the value purpose. Are you getting the point? Okay, that means since we are going to use A to Z letters, right? A to Z, A1, A, B, C, something like X and Y and Z also we can write. Okay, that means if you want to represent the two lines, for example, this is the variable, and this is the black box. I'm using here is X, and this is the Z, and this is, for example, Y. Can I write like this? Yes, of course. This is the one. X is one variable I'm giving. Z is one variable I'm giving. Okay, but unfortunately, in the very logo, we are going to use X and Z for the purpose of value purpose also. 0 and 1 comma 1 value purpose also we are using. Okay, so if you're using the capital X and capital Z is not a problem actually, because the Verilog is a case sensitive. Definitely 0 and 1 and the small x and small z meant for values. Okay, but never don't try to use that X and Z for the purpose of variable declarations. Okay, my recommendation should not be. Values also should not be honest. Definitely, we don't give this, especially this case that we have given. For the default values, I want to keep it as all. Okay, but generally we take all zeros or all ones. So. Okay, but whatever you see that it is not your answer. Okay, this is not for the answer for the exact values of your input variables. Okay, right. So therefore now we are going to, as I mentioned, that this is what the recommended approach I'm going to use, MSBT LSB. Okay. So let us modify this one. Can someone help me? What is this particular A here now becomes? A and B values. What is this value? What is this variable? A of 1. Very good. This is A of 0. Okay. Next. What about this one? D of 3, D of 2, D of 1, D of 0. Why? Because what is the D here now? D is actually 3 down to 0. Okay. D is actually from 3 down to 0. Okay, that means 4 lines will be available. Is it clear? So now here also, let us go and write the program also. How do we change this in this program? Let us go and modify this one as well. Okay. So see, the beauty of this one is you can write here is A directly here, A, comma D. Are you getting this point? Look at this one. Simply A and D. But when the input is declaration, I should mention what is the size of A, what is the size of B. Sorry, D. Okay. So let me go and write. Let me go and remove this portion as well. Okay. Now, can you help me? How do I write like this? Here, look at this. Carefully, you have to write like this. So 1 down to 0 of A that I have to write. This is how we need to write. A of 1 down to 0 should not write. While both declarations, we have to write in this way. 1 down to 0 of A. That means A is a 2-bit line. A is a 2-bit line. Okay. Similarly, here how can I write like here? 3 down to 0 of D. Like this? Right. Next. Now here also we have to change. Okay. But in this small program, it will be a little bit difficult to write all these things. But definitely when we are talking about the very big modules, this vector notation is essential and everybody mandatory will use this for the simplicity of represent the variables. Okay. Okay, quickly let us modify this program as well. So what about the D naught here now? In this case, we want to talk about the D of 0 here. Next, this is the D of 1 here. Okay. I think better I can use a different color so that it will be identified. D of 0 here, D of 1 here, D of 2 here, D of 3 here. Okay. Right. What about the D of 1, D of D naught? What is the D of D naught? Okay. This is the naught of A of 1 logically ended with naught of A of 0. So this is how I need to write. Is it clear? Similarly, I'm going to write the other things as well. Okay, I'm going to give the time. Now, naught of A of 1 ended with A of 0. Okay. Next, A of 1 ended with naught of A of 0. Next, A of 1 ended with A of 0. Hopefully, you catch this point, right? Okay, right. So therefore, the same thing that you have to follow for the gate level modeling, same thing that you have to follow for the behavioral modeling. Okay. So now the advantage of using this behavioral modeling is something like this. Okay. Okay. Instead of writing the concatenation, what I can do? Can you please let me know what is the concatenation? Okay. Of course, here also simply I can write A here. Look at the board. Okay. A here. What about here? A here. Okay. Now A is actually 2-bit size. Okay. You have to mention the 2-bit size anyway. But okay, let me modify because this is what we are interested to write in this way, right? Okay. Now, what about this one? Simply, you did not worry about this one. Instead of viewing this one, just write D. Right? D is actually already declared as a 4-bit size. D is already declared as a 4-bit size. Therefore, now directly I can use the D input. If this point is clear, no confusion, right? Okay. Similarly, here also, by default, D is required. See, in the behavioral modeling, how effectively that we are able to write, right? And one more thing is that here also, of course, definitely we are writing here, but the register 3 down to 0 of D that we have to write. Okay. And definitely, of course, this also we change. That is actually uh, uh, 1 down to 0. Okay. And of course, these things can be removed and this should be A comma. Okay. Right. So this is one thing. And basic circuit, the basic approach I have done. And then second part is vector notation that we have seen. And the third part also I want to tell you, because we are going to see that the structural modeling in the next lab. What is that one? See, generally, if you want to design 3x8 decoder by using the 2x4 decoder, okay, my requirement is something like this. What is my requirement is 3x8 decoder using 2x4 decoder. Okay. Okay. So what we have to do here? So first of all, we have to take the 2x4 decoder. Okay. That means the two by four decoders I have to consider, right? Two by four decoders I have to consider. Okay. And then I have to produce this is producing four output lines. This is also producing four output lines. But how many we have to take here? Only two input lines. Only we have two input lines. So far we have seen this one only. Two input line, four output line. But actually, when we are realizing the complex circuits like this, 3x decoder, but only 2x4 decoder is not sufficient. Okay. So we have to use the extra line here, extra signal. This is also called enable signal. Okay. This is called enable signal. With the help of the enable signal only, we are able to realize this one. Okay. That means you take this is the two input line, right? Just we have to combine these two input lines and take this is the line and invert it and give it to this one. This is called actually, it's a, yeah, this is a two line. This is actually three input line. This is a three input line. It is a eight output lines. This is how we have to do it. Okay. But unfortunately, we have realized only two input related 2x4 decoder only we have used. But we have not mentioned the enable, included the enable signal in the 2x4 decoder. Okay. Let us add the enable signal to it, and then we are going to. Okay. So quickly, let us look at that one. Okay. But the sake of simplicity, I'm going to consider this is the truth table. Okay. Okay. Let me take this is the truth table. Okay. Copy. Let me copy here. Let me modify this particular truth table. Okay. Okay. See, look at this one. Enable signal means that this is what the enable signal. Okay. If the enable signal is 1, then only whatever you apply the input signals, that will show you the output. Okay. That will show you the output. If the enable signal is not there, for example, okay, irrespective of whatever the input it is, irrespective of whatever the input, the output is 0. All zeros, let me write it in this way. All are zeros. Did you catch this point? If the enable signal is 0, don't expect any output. Okay. If the enable signal is 1, then based on the input, we will see the output. Hopefully catch this point, right? Okay. But now, how do we generate the mathematical equation and then hardware and then done everything? First, let us develop the mathematical equations. What is the mathematical equation for the D naught? That means this is also included, right? This is also included. Therefore, simply we'll write D of 0 is nothing but, okay, A bar, B bar, and E. Am I right? Okay, small e or capital E doesn't matter. But let me write the small e. Let me write small e better. Okay, this is the small e. Okay. Now what about D1? D1 is A bar, B dot E. D2 is actually A dot B bar dot E. D3 is nothing but A dot B dot E. Am I right? Now what is the program now here? What modification that I have to do in this program now? I have to include the enable signal also. Okay. So better first my request is that first you write all the inputs, then we are writing the outputs, right? Okay. Now we have to include E also. Now we include E also. But I'm going to go and use another color. But we write E also. Okay. Now we write here another input. Okay. Let me write another input. Can I write here at this place? Input? Yes, because after the semicolon, it's a new statement. Input E. Why can't I write the input 1 down to 0 of A comma E? Why can't I write, just put a comma here and write it like this? Because A is actually 2-bit size, but E is a 1-bit size. If you write A comma E, if you write like this, then A is a 2-bit size, E also 2-bit size. It becomes. Okay, we don't want that one, right? A is a single bit size. That's the reason why we don't use this particular thing, right? That's the reason why we write E. Okay, simply we can modify this program. Okay, just simply remove this and E that we can write. Okay, and this is how we need to write the program. And E and E and E. Okay, got this point? Okay. So now you can modify the gate level modeling. Similarly, you can modify the behavioral modeling also. Okay, and try to design this 3 by 8 decoder by using the structural program. Structural programming, because already we have written any one of the style, then you can just call 2 times, that's enough. Structural modeling is over, right? We stop here today, and please try to execute these programs in your system. Okay. What it is, where it is, that yes, I'm going to